Okay, good afternoon. Welcome to the online BTech lab courses, and today we are going to see how to perform this coupled pendulum experiment. So the experiment essentially consists of two pendulums which can move independent of each other like this, and this movement is just because gravity is acting downwards, and you know how to find out the time period of these two independent motions. Now the goal of this experiment is not really to measure the independent motion, but to connect these two independent motion through a spring whose natural length or the unextended length is this. So this is the unextended length, and now if I essentially keep this one fixed and move this a little bit, the spring is getting extended, and you see that slowly the motion of this pendulum is affecting the motion here, or in other words, the energy is getting transferred from this pendulum to the other one. So this is precisely what we are going to measure. We are not really going to measure the energy transfer, but we are going to measure a related concept, and this is the concept of resonance or the beat frequency. And we will explain this a little bit later in the board. So why we are doing this? So why this kind of system is important to study? So as I emphasized in your BTech theory classes, simple pendulum or simple harmonic oscillation is one of the basic building blocks of almost all physics that you see around it. So from classical systems like this one, which is oscillating because there is gravity downwards, to quantum systems where you have a lattice and then there are atoms in the lattice, they will essentially vibrate. And even if you go to much larger scales like the universe itself, that itself vibrates. So everything interesting in the nature actually gives you vibrations, and there is a very good reason for it, because as a physicist we can only solve very few problems analytically. Simple harmonic oscillation is a very good approximation to a lot of physical problems where you have a potential and you are essentially sitting at the bottom of the potential and slowly moving. So this is a very common setup in physics, and that is why this kind of oscillations are very important. And this is also important because it is not that simple. Yes, if you do not have the spring, then oscillation of this pendulum by itself is quite simple. You know how to do this. But when you couple this with the spring, you now have a whole new thing where the motion of this is essentially bringing motion to the other pendulum. You can again connect another pendulum here with another spring. It will transfer energy from this two motion to the third spring, and so on. So you can basically create chains of such pendulums with connected springs, and they will essentially oscillate in various kinds of ways. So here in this experiment we just have two pendulums, and we will see that there are essentially two different frequencies with which this whole system can oscillate. Also, again, in your BTech theory class you are familiar with how to solve this kind of system. This is the system of normal modes. So you will find two normal mode frequencies for this system. So in case you have forgotten, I will again go to the board and explain it to you. So let's go to the board and see what are the different kinds of motion that is possible with these two pendulums connected by a spring of some spring constant K. Okay, so now that we are in the board, let's see how to write down the equation of motion for the coupled pendulum. So first we will cover this side, and then we will basically see the three important cases of the motion. So let's see. So at rest, you have this pendulum and the other pendulum. Let's call it 1 and 2. And then there is the spring connecting these two pendulums, which is at rest. So it is unstretched. Now let's say that you move this bob by a distance y and move this bob by a distance x. So these are all small y and small x. Gravity is acting downwards. So as you do this, this whole spring will basically get extended by an amount x minus y. So now that the spring is getting extended, it will basically create a restoring force k into x minus y, or minus of k into x minus y, depending on whether you are writing down the force for this pendulum or writing down the force for this one. So the equation of motion are pretty standard. So this is the acceleration term. This mgx by L is the term coming from the gravity. So this is the usual oscillation that you know without any spring. So if you just do not have the spring and you just have this pendulum and this pendulum is oscillating, then the equation of motion you will be mx double dot equal to minus mg x by L. So this x by L is essentially just this angle theta 1, which is basically just the small angle approximation of sine of theta 1. So this is just the component, g sine theta component of the gravity. And then on top of that, there is this force minus k x minus y, which is acting as a restoring force on this x1. Similarly, for the y also, you can write down the part, which is essentially again the gravity part, but then there is plus k x minus y. Notice the minus here and the plus here. So if the force is along this direction, then the force or the tension is along this direction on the other pendulum. So that is why there is a minus, there is a plus here. Now you might think that how to solve this kind of differential equation. It is obviously a second order differential equation. Each of the equation you will need two initial condition. You have to basically specify the position and the velocity of the moment of this pendulum, either this one and this one at time t equal to 0. So in total there are 4 initial conditions. But you also see that in writing down this equation of motion, you have x here and you also have a y here. If you didn't have the y, then it is very standard thing and you could easily write down what is the motion. It is just simple harmonic oscillations. But because you have this y, it is little bit difficult. But it is actually not difficult. So whenever you have a system, a two-body system like this, it is often more useful to go to another frame of reference, which is essentially the center of mass frame of reference and the relative frame of reference. So you basically define big X, which is the center of mass coordinate x plus y, and the big Y, which is essentially the relative coordinate x minus y. Now in terms of this big X and big Y, these two differential equations can be written as big X double dot plus some omega naught square big X equal to 0, y double dot plus some omega naught square plus 2k by m y equal to 0. Now you see that there is no mixing of variables. So there is no big Y here, there is no big X here. So this is a simple harmonic oscillation in its own right, which is oscillating with frequency omega naught. So this omega naught is essentially just the natural frequency of oscillation when you do not have any spring. And then you have this other oscillation for the relative coordinate, which is omega 1, which is omega naught square plus 2k by m whole square root. So here you will see the effect of adding the spring. Because you had this spring, this frequency is now greater because it is pulling the pendulum towards it. So you now have these two differential equation, but knowing just the differential equation is not enough. You also have to know what are the initial condition or different initial conditions you can put to solve this differential equation. So we will see three interesting cases on this side of the board. So let's say this is the case 1, which we will call the in phase, where at time t equal to 0 you choose your coordinates x and y such that x is equal to y. So once you, and this basically means that the big Y, which is the relative coordinate, that is 0. Now this is something that you are fixing at time t equal to 0. But you will soon realize that because of the nature of this differential equation, once you fix those conditions at time t equal to 0, they remain for all times. So for all times y will be 0, and for all times the small x will be equal to small y. So this is the motion where essentially these are the two pendulums and they move in sync like this. We will see in a moment the actual motion when we go again back to the experiment. The case 2 is the out of phase, and which is exactly opposite to the in phase. So here we will put the big X to be 0 and the small x will be equal to minus y. This is again a condition that you put at time t equal to 0, and you will again find that this is true for all times. So this kind of boundary condition essentially means that if you have these two pendulums here at time t equal to 0, they move like this. So they are moving out of sync. So they are coming together and then they are going away, they are coming together, they are going away. So these are the two motions, but the most interesting one is the case 3, which is the resonance or the beat. So here what we will do, it is at time t equal to 0, we will keep this pendulum which is marked with displacement y as with y equal to 0. So we will basically not move this pendulum and then move the other pendulum by a distance 2a, thereby stretching the spring by 2a. Okay? So once you do that at time t equal to 0 and leave the system, what you will find that this oscillation of this pendulum slowly get transferred to oscillations of the other pendulum via this spring, because this is getting stretched and compressed continuously, so it is transferring energy from this oscillation to this one, and again this oscillation will slowly pick up and then start transferring energy back to the other oscillation, and this phenomena will go on for infinity, but obviously there is damping and etc. So at some point it will stop, but in ideal situation they can go till infinity with this kind of to and fro motion. So how to write down the equation of motion for this? Now it is an exercise for you that put this boundary condition here and find out what is the solution. So you will find that the solution is big X is equal to some 2a cos omega naught t, and big Y is equal to some 2a cos some omega 1 t. So omega 1 is essentially the other frequency which has this 2k by m part. So once you have this big X and big Y, which essentially are called the normal modes, you can figure out what is the small x and small y. So the small x is essentially half big X plus big Y, which when you put these values and calculate comes out to be some 2a cos omega 1 minus omega naught t by 2 cos omega 1 plus omega naught t by 2. And similarly, the cos will be replaced by sines for the y. So what is this kind of a motion? So this is one sine with some frequency multiplying another sine with some other frequency, and you will notice that obviously omega 1 plus omega naught is a higher frequency than omega 1 minus omega naught. So this is oscillating much faster than this one, which is basically going something like this. So we will call this one the envelope. So this is the slow oscillations, and the slow oscillations we will call the envelope, and the faster oscillation we will label it by WC, which is essentially the resonance oscillation. So how does this plot look like? So this plot essentially looks something like this with time. So this black line is essentially the oscillation of the envelope. This is the smaller frequency. And on top of this smaller frequency, there is this higher frequency, which essentially is this blue line. So, but the maximum heights and maximum lows of this blue line are capped by the envelope. That is why this is called the envelope. So you will see this goes like this, the blue line, and then come here, the ends here, again goes like this, ends here, and again start and carry on. So in one oscillation for the envelope, there are several oscillations of the blue line, which is this frequency. You will also notice that the zeros of the blue line and the black lines are kind of matching. Now this is an ideal situation when the ratio of the frequency W1 plus W0 divided by W1 minus W0 is an integer. So the ratio W1 plus W0 divided by W1 minus W0 is equal to an integer. If this is not an integer, then these zeros will not sync with each other. What will happen is that either this one will undershoot like this, either this one will undershoot like this, or this one can overshoot like this when the black frequency is coming to 0. And this is exactly what you will see in the computer plots of this experiment. Though all the values of the spring constant, mass, and the length of the pendulum is adjusted so that this ratio comes out to be integer, but again this is an experiment, so nothing really is without any error. So because of some error, you will always see that the zero of the black and the zero of the blue line will not match each other, but either it will overshoot or undershoot. Okay, so this is the phenomena of beats, where you basically have a envelope frequency, which is the smaller frequency, and then inside that smaller frequency there is a bigger frequency which goes like this. Okay, so now let's see, once again go back to the experiment and see these three phases, and then we will see the procedure. Okay, so as I explained in the board, the three cases, let's quickly see how does they look in the actual setup. So the case 1 is essentially the in phase one, where these two pendulums will essentially move together like this. So you can see that the spring is not really getting extended or getting compressed. So the spring essentially has no purpose here. So this is one such oscillation. So this is exactly the same as normal simple harmonic motion, and this is not that interesting. The other one is if we take them a little bit apart, thereby extending the spring, and then they will come together, go out, come together, go out, and you can see that the spring is getting compressed and getting extended, compressed and getting extended. So this is essentially the out of phase motion. The third one, which is the most interesting one, is this the resonance, where you will keep this one say fixed and stretch the spring a little bit and Now you see that the constant extension and compression of the spring is transferring energy from this pendulum to this one. You see that this one has more or less stopped and this is now active. This will now stop after some time, and again this will become active, and again this will stop after some time, and this will again become active. So there is a transfer of energy through this spring, so the compression and extension of the spring for each of these two pendulums. Okay, so now that we have actually seen what are the three cases of the pendulum, we will now start with the procedure of exactly how to take readings and how to do the calculations and so on.
Now we are going to explain the procedure of the couple pendulum. These are the apparatus of the couple pendulum setup. And this is the system, and this is the power source, this is the interface. What we are going to doing mechanically, it is observe taking the graph in the system. First we open the system. After that a measure software is here. Right click the measure software, then we go to the file, then new measurement click. A box is coming, then we click the continue and keep the cursor in the start measurement. After that, in the in phase mode, we just showing to you how can we oscillate and record the data. First we check both the bulbs are in parallel conditions or not. After that we should check the extreme point of the spring, both are in equal level or not. After that the both are checking, it should be okay. Then we take in the left hand we should hold a stopwatch, in the right hand then we hold the mouse. First in phase oscillations from the bottom end, we just shifting from their displaces from their normal positions like this. It is not necessary to take immediately the observations. In that cases, that is 3 and 4 oscillations is missing, that is no problem. Then after we set on our mind, then keep our right hand on the mouse and the start measurement click and the stopwatch, both are in simultaneously click and counting 20 oscillations. After 20 oscillations, then we should stop the stopwatch as well as the graph, and this graph is display in the monitor. We should save like that is MS Word, that is Control S, and that is name, let it be 1 2 3, and save this one. This type of a graph is coming. This is in phase mode. It is right or wrong. We should also check that is in phase means that is the degree, that is no phase difference, that is the zero phase difference, the like the pattern is coming. This is in phase mode. After that we should going to taking the observation of the out of phase. In the out of phase, that is first we check, like already we explained, that is in the in phase mode, that is the both extreme point of the spring is in equal level and the bob is in parallel conditions. From the bottom end, both are bring from their normal positions towards each other, very little bit displacement after remove our palm. Then like in phase mode, we also that is open file, then new measurement, then continue and start measurement, and whatever time is coming in the out of phase mode and the graph also that is coming from the monitor, both should be record. This is the graph of the out of phase mode, and this is the time period of the what it is observed from the stopwatch. We should write it in the box provided, that is out of phase that column, that is first we take that is 20 oscillations for T1, then another 20 oscillations for T2 and T3. Like in phase mode graph and the out of phase cases, we also save that graph, that is any name, and this is complete, that is out of phase mode. And in the case of a beat measurement, first like in phase out of phase, we should go to the file, then new measurement and keep the cursor continue, then keep the cursor in start measurement. In the case of a beat measurement, that is both the pendulum that means one pendulum bob, one pendulum is keeping constant, the second one bring from their normal positions and remove the palm. After some time, the displaced pendulum coming to any, that is a rest positions. On that time we start the graph as well as the stopwatch. That starting point, the first stop is including, that is your first stop. After that the second stop is coming, this pendulum, then third stop, then fourth, and then fifth. When it achieves the fifth stop, then we should stop the both stopwatch as well as the graph. The graph is coming like this, that means this is the stop positions and this is the another stop position. This is the envelope is coming like this, and this is we are taking also, that is 3 times, that is T1 for the 5 stop and T2 for the 5 stop and T3 also 5 stop. This is the time period of the beat. Like this we also save, that is in phase and out of phase mode. Then we save, that is our name. Then we should open for, that is the resonance time period, then file and a new measurement, then continue and keep the cursor in the start measurement. Then in this resonance cases, that is one pendulum is in a stop conditions and the second one displaces from their normal positions. After some time it will come to the stop conditions, the displaced one. Now this one is in stop conditions. Again, when it starts displaces and achieves the maximum amplitude, on that time we count, that is 5 oscillation, that is 1, 2, 3, 4, then stop the measurement, stopwatch as well as the graph. The graph is coming like in the displays in the monitor, and the time is coming, that is 10 point something, and this time we should note it, that is the column provided in the resonance table. And like this we also taking, that is 3 times, that is T1, that is one resonance time, and T2, that is another resonance time, and T3 the last one. After completing all this graph, then we should taking the printout of the in phase, out of phase, and beat and resonance. Taking all the observations from the stopwatch, we should note it in this table provided in the manual. Then after taking the print of the graph already saved in the monitor, then we go to for the calculations. In the calculation part, that is in phase mode time, that is the formula is 2 pi upon, that is omega naught, that is square root upon G upon L. By the measuring tape we should taking the measurement from the point of suspension to the center of the bob. This is the length, and G we acceleration due to gravity we know. This is the in phase time period, and out of phase time period, that is T1 equal to 2 pi naught omega 1. Omega 1 is, that is the formula is omega naught square plus 2k upon am. K is our, that is spring constant, that value is 1 Newton per meter, and a mass is the mass of the bob, that is 1 kg. And already the value of, that is omega naught we should calculate, that is G upon L square root, and putting all this value and calculate, that is omega 1. Then time period for beat is 4 pi upon omega 1 minus omega naught. Omega 1 and omega naught already calculated and put it here, then we can get, that is time period of a beat time period. And the resonance cases also 4 pi upon omega 1 plus omega naught. Omega 1 value, omega naught value, put it here, and we get the value of the resonance time period. After that we should take the printout which is already saved in the monitor, and that printout we should calculate the time period from this graph, and that value and this calculated value we should compare and calculate the error calculations. This is all about the procedure of the coupled pendulum.
Okay, so now that you know the procedure of how to do this experiment, we will essentially take for you a completely new set of data. We are not showing this in the video, but we will take a completely new set of data. This data will be provided to you, and you have to essentially process the data. That is, you have to basically do all the calculations that are there in the manual, plus the error analysis, and you should also write some comments about what are the various places or in where you can basically find a coupled system like this, whether you know some application, engineering, science or otherwise, and if possible think that what kind of difficulties can you face while doing this experiment. It is difficult in the sense that you are not really doing the experiment here, but still from the procedure that we explained, try to think of some difficulties that you could possibly face if you are the one who is doing this experiment, and also write about it. And that will essentially complete your lab manual part of it. And okay, thank you. And